The voltaic cells discussed so far do not look too much like the cells we put on our watches or cell phones or MP3 players. That's because we actually use dry cells. Smaller cells based on the same chemistry but using an electrolyte that is a paste instead of a liquid. Shown in this picture from your text is a D cell. The D refers to its size. Most dry cells we buy are 1.5 volt cells. Place several of these cells in series so that the negative electrode of one cell is connected to the positive terminal of the next cell, and so on. We create a battery. We usually refer to dry cells as batteries. You can see now this is technically incorrect. 6 1.5 volt dry cells in series is a 9 volt battery. In the dry cell shown here, oxidation occurs at the zinc electrode and reduction at the graphite electrode. Since graphite is the conductive but non-reactive component of the dry cell, the oxidizing agent is obviously in the electrolyte paste. An alkaline dry cell, as shown in your text, shows the electrolyte is a very alkaline or basic paste. Manganese oxide and water combine to form a strong oxidizing agent, while the zinc metal in a hydroxide paste forms a strong reducing agent. Button cells are much smaller than alkaline cells. Used in watches, hearing aids, and pacemakers, they still generate a similar amount of electrical potential energy. The zinc metal in hydroxide still makes an effective anode, but here the cathode is either silver ions or mercury ions. The safe disposal of expended dry cells, even button cells, should be an important consideration. Heavy metal contamination of the environment is a growing concern. Mercury-based cells release toxic mercury metal into the environment. Silver-based cells may be less harmful, but are usually more expensive. Consumers should be asking themselves, what is the environmental impact of me purchasing this type of dry cell? A fuel cell is a voltaic cell that has a continuous flow of reactants into the cell and products out of the cell. The combustion engine of a car has a continuous flow of gasoline into it and a continuous flow of gases out of it. However, the fuel cell differs by converting the fuel directly into electrical energy, making it more efficient and cleaner than engines that burn carbon-based fuels. In the hydrogen fuel cell, the waste product is pure water. While not a new concept, it is only recently that the technology has advanced enough to enable fuel cell application in practical devices. This city bus in Vancouver is part of a development program, but if fuel cells are more efficient and cleaner, why are they not more widespread? To generate a cost-effective fuel cell, production would have to be significant. At the moment, the cost of this technology is far too expensive for wholesale application. I have an asterisk next to the environmentally friendly bullet because while the waste product of a hydrogen fuel cell is pure water, the source of the hydrogen is provided by the conversion of ethane to ethene by the petrochemical industry, an expensive process and one that requires a lot of energy. At present, this energy comes from fossil fuel combustion, countering the ecological benefits of the hydrogen fuel cell. Your book gives an example of a proton exchange membrane fuel cell, first used by NASA and currently being developed for cars and buses. The anode of this fuel cell is porous carbon coated with platinum. The incoming hydrogen gas is oxidized, forming hydrogen ions that flow through an electrolyte, while the electrons move through the external circuit to the porous cathode electrode. Finally, oxygen in the air passes beside the cathode and combines with the electrons from the external circuit and the hydrogen ions in the electrolyte to form water. These are the reactions that take place at the electrodes. The hydrogen ions are shown as having a solid phase because they bind to the solid membrane as they pass through it. There are other fuel cell designs that use alternative materials to make the cells more efficient. The one we've outlined, the PEM cell, is about 40 to 50% efficient, or use a more accessible fuel source. One fuel cell being developed uses methanol, While the overall reaction looks similar to a hydrocarbon combustion reaction, the direct methanol fuel cell produces more energy and releases less carbon dioxide.